Okay guys, so as you can see today we're going to do 1.3 transformations of functions. So this should all be a review from Algebra 2 or Algebra 2 Honors, where we did functions all throughout the year. So hopefully this won't take too long to get through. So the first function we have up here, f of x, which remember is synonymous with y, so you could just be putting y here. Y equals a times the quantity x minus h squared plus k. So this particular parent function I threw up here is actually for a quadratic, right? And we'll remember some things about a, h, and k, which is written down below. But the function we were given is a quadratic. Okay, and its graph, of course, you're probably familiar with the name, is a parabola. And its general shapes, when we have an upwards opening parabola, looks something like that. If our a value is negative, we might have an upside down parabola, to excuse my drawings here. And then we have these kind of critical points on our graphs, the minimum or maximum points, which is our vertex. Okay, and in a lot of parent functions, that value, that critical point where h and k will be located, is usually a vertex. Sometimes it's just a critical point or a starting point on a graph, but it's always some sort of critical point. Okay, so for this particular one, the values of h and k, which is what's being added or subtracted inside, added or subtracted outside our function, is that critical point h and k. Okay, so to remember some values here about a, this multiplier outside. If a is negative, okay, that's giving us this upside down graph. We call that a reflection over the horizontal axis. Okay, so over the x-axis. This is actually a very nice picture of what's happening. If we had our x-axis here, we're reflecting over the x-axis. That's what a negative a value will do to our graph. Flip it upside down. If the absolute value of a is greater than 1, this means regardless if it's positive or negative. Okay, if it's positive, our function's opening in the same way as the parent function, or upwards. If our a value is negative, we know it's opening down. Okay, so a way of saying we don't care about the sign, whether it's positive or negative, is absolute value. So if the absolute value of a is greater than 1, so if a is 2 or negative 2, 3 or negative 3, any value that's bigger than 1 or technically less than negative 1, okay, that gives us a vertical stretch. Okay, it's not a horizontal stretch. I wish I could have done this more vertically and fit it in here, but it is a stretch in the vertical direction. So imagine kind of pulling something apart in the vertical direction, it's stretching it out. Okay, that makes it thinner than the parent function. So if my parent function parabola looked like that, our thinner one might look more like that. Okay, that might be more of a vertical stretch than our parent function. Okay, if the absolute value of a is between 0 and 1, okay, a can't be 0 or we lose our whole function, but if it's between 0 and 1, so for instance, if a is 1/2 or 1/3 or 2/3, any value that's between 0 and 1, it could be positive, it could be negative, any of these values this would apply, it gives us a vertical compression. So again, that's in the vertical direction. So if I normally had a parabola like this, and it's compressed in the vertical direction, it might look more like this. Okay, we're kind of taking it from here and here and squishing it down. Okay, and that gives us a flatter or wider looking parabola or whatever function than our parent. Okay, so there's our first part. Okay, here are some of our other functions. Up top we have our absolute value. This is absolute value. Apologize here, I'm clicking some wrong buttons multiple times. There we go. Absolute value. And we know it's an absolute value function because x minus h, this kind of main part of our function, is in absolute value bars here. So this is absolute value. You might remember the shape of this graph. The v in value is a good way to try to remember it. It's a very v-shaped graph. And this point is called a vertex. And that's where h and k will be. Okay, so here is if my a value is positive, it opens upwards. If a is negative, it might be upside down. But this is our vertex h and k. Our next function, this is our cubic parent function, our cubic transformation here. We know that because x minus h is being cubed. So if you remember the cubic shape, kind of S shapes through the origin. And at this point, it's not a vertex, but it is a nice critical point on our graphs, kind of where it's going to change directions here. So this would be if a is positive, it opens up and to the right. And if a is negative, of course, we get a graph that is reflected over the x-axis and looks like that. It goes down and to the right instead. Okay, but that critical point there, it's not called a vertex, but it is still a critical point on our graph, is where h and k will be. We can get them from these two values. And our last one is our square root function. I guess I should have written this in, cubic. Okay, and our last one is our square root function. And there's cube roots, extra roots. We're just going to stick with square roots for right now. And our square root function, you might remember, kind of starts at the origin, and it's a half sideways parabola. Okay, it does keep going up and to the right. And that starting point is where h and k would be. And of course, if we have a negative a value, if it gets reflected horizontally or over the x-axis, we should get something that goes like that. It goes upside down. Okay. Again, our a values can stretch or compress any of these. H will shift horizontally, so left and right, because we're changing the x value of this critical point. And k will move our graph vertically, shift us up or down. We're changing the y coordinate of our point. One last thing to add in here before we move on to some more examples. You might remember when you identify h and k, that h, because of the kind of the negative sign in the formula here, is always the opposite of what it appears to be. So what I mean like that, let's say we had this example, 2 times x plus 3 squared minus 4. So first of all, think about what type of function this is. Is it absolute value, cubic, square root? Is it a quadratic? Okay, in this case, it's definitely quadratic. We've got our quantity here being squared. So let's identify a, h, and k really quick. So our a value is out here. It's our multiplier. A is 2. And then h and k, we do actually have values for both of those here. But if you remember, h is kind of the opposite of what it appears to be in here. H is actually negative 3. And that's because of this negative sign. What we're really looking at is x minus negative 3. If you thought about simplifying that, minus a negative becomes plus a positive, which would simplify to just x plus 3. Okay, so and some weird reasoning. An easy way to memorize is just that h is going to be the opposite of what it looks like, the one inside the function. Okay, so h is actually negative 3, which means, are we shifting left or right 3? We're going left here. So that critical point, in this case our vertex, because it is a quadratic, will be moved left 3 from the origin. And our k value out here, it's just plus k, so we don't have to worry about switching the signs. K is negative 4. So is that going to move me up or down 4? Because it's negative, we're going down. Okay, lastly, coming back to a, if my value here is 2, so positive means, do we have a reflection over the x-axis? No. What does that 2 do to my graph? Does it stretch it vertically or compress it vertically? It's going to stretch it by a factor of 2. In fact, it's going to be twice as tall. All my y coordinates will be doubled from the parent function. All right, we're ready to move on to our next examples. Okay, it says let c be a positive real number. Okay, so c is just a positive, any real number. Describe the transformation for each parent function f of x. All right, our first one here, my function, we're just adding c, and this is outside or after the function. So in this case, our c from our main function form here, just as a reminder, a times x minus h plus k. In this case, when I have something being added after our function, it's acting like k. So if this is a positive real number, plus c is going to shift up c units. Okay, so what do you think is going to happen to f of x minus c? Again, if this minus c is outside or after our function, it's also a shift, but now we're going down c units. Okay, so adding or subtracting outside the function is going to shift us up or down. It's acting like k. Okay, our next part here. What about if I'm subtracting inside? So now we're talking about inside our function. We're talking about h. And remember that it's going to be kind of the opposite sign here. So if it's minus c, are we going to be shifting left or right? This is a tough one. In this case, we're actually shifting right c units. Again, remember, it's going to be kind of the opposite sign of what it looks like in here. So think positive c, and positive would mean to the right on our graph. Okay, what about if it's plus c? Should hopefully be a little bit easier. It is also a shift. Think opposite sign of positive c would be negative, and that means negative in the x direction, so we're shifting left. Okay, what about if I have a negative sign in front of my function? What is that acting as up here? In this case, we're acting like a. So in this case, if a is negative, we have a negative multiplier in front of our function. That's going to give me that reflection over the x-axis. Okay, I threw this one in here. This is a tough one because we didn't really talk about it in the previous slides. Maybe we'll come back to this last. What if that multiplier outside is a 2? What does that do to my graph? Okay, a positive 2 doesn't do a reflection, but it does give us a vertical stretch. Okay, and that is by a factor of 2. And then what does this 1/2 do out here? So now we're between 0 and 1. In this case, this is a compression vertically. And technically, when you talk about reflections, you would do the reciprocal. So you could say this is a compression by 2. But just to keep it simple for us, we're just going to say it's because a is 1/2. We're not going to get too technical there. So let's come back to this tougher one here. If a multiplier outside of our function reflects me over the x-axis, what do you think a negative multiplier inside of our function does? So this time that it's applied to x, our input value. Kind of led you on there a little bit. But if you guessed this, kudos to you. It is a reflection over the y-axis. So we take a point here and reflect it over the y-axis. Or if I had maybe a square root graph, it might be reflected going that way. Okay, this is the y-axis. So that's what this would do. Tough one, but a good example to talk about. You may see that. I don't think we're going to test too much on that, though. Okay, last couple of examples. I'm trying to keep this video short, so feel free to pause and go back and write stuff down as you need to if I'm going too fast for you. Okay, compare these two graphs. To compare our two graphs, it's giving me a graph here, and it wants me to compare it to the parent function, it looks like. Okay, so to compare these two, let's talk about what these values are and how they compare to our parent function. So let's identify a, h, and k. And that will help me describe these transformations or the difference between these two graphs. So first thing I look for is a. Do I have any multipliers on my function that has x inside it? And it looks like we have a -1 out here. Okay, so that gives me some idea what that does to my graph. What does a negative value do to my graph? Reflects over the x-axis. Is there any vertical stretch or compression here? In this case, the answer is no. If it's exactly 1, it's the same kind of width or narrowness as the parent function. H, is there anything being added or subtracted to x inside of our square root function? And in this case, the answer is no. So you can think of that as x plus 0 inside of there, or that there is no h value. So we have not shifted left or right at all. And then this minus 1 that's after my function, after the square root, is acting as k. And remember that k we don't need to change the signs with. That would have been h if there was a value in there. And so k is our vertical shift. In this case, rather than write out vertical shift, we're just going to say we shifted down 1. Okay, down because it's negative and 1 unit. Okay, there we go. We compared our two graphs. This graph has just been reflected over the x-axis and shifted down 1. Otherwise, it looks like our parent function of a square root graph. Okay, example 2. Describe the transformations that will yield this graph. So here I see x minus h is being cubed. So we're working with a cubic function. And it looks like it's giving me the parent function y equals x cubed. So it's essentially the same question. So let's find a, h, and k for this particular one. Okay, so a is our multiplier in front of our function, which is negative 2. Negative, again, gives us a reflection over the x-axis. But this time my value is not 1 or negative 1. So what does this 2 do to our graph? Is that a vertical stretch or compression? And it is a stretch. We're larger than 1. So it's a vertical stretch by a factor of 2. Okay, next let's find h and k, which has to do with our shifts horizontally and vertically. In this case, there is something being added or subtracted inside the cubic function. And this is going to help me identify h here. So remember that h is the opposite of what it looks like. So h is really positive 4. So horizontally is positive left or right on our graph. And in this case, it is right. We're going to shift right 4 units. And then outside, after our function, is there anything being added or subtracted? In this case, there isn't. You can think this is being like plus 0 after our function. K is 0, so there is no vertical shift. Okay, one thing to be on the lookout for, though, as you see some more examples, we'll do some more examples in class, obviously, is sometimes you might get, they might try to throw in an oddball to you, something like this. Okay, where be careful, this 5 is not being multiplied by our function. In fact, what is being multiplied by our square root function would be like a negative 1 here, right? An easier way they could have written this to not confuse you would have been the square root of x plus 5 if we changed the order of these two things being added or subtracted. Sorry, negative square root of x plus 5. Okay, so the a value here is really negative 1. It's that negative sign that was in front of the radical. And this 5 on the outside is really our k value. So sometimes they'll throw in this kind of opposite order. Don't let that throw you off. We'll go through some more examples in class. Thank you guys for listening.